So, very good evening, everyone, and welcome to the NPTEL's first live interactive session on the course Mechanical Behavior of Materials, Part 1. The course instructor for this course are Dr. Shashank Sekhar and Dr. Sudhanshu Sekhar Singh from the Department of Material Science and Engineering at IIT Kanpur. And I am Shivam Jaiswal. I am a research scholar in the Department of Material Science and Engineering at IIT Kanpur. So, in this live interactive session, we will be going to solve some sample problems related to your weekly assignment and some concept related question, which will in turn will help you to solve your weekly assignment. And also we will discuss the what are the contents that are covered till the last week, okay, like in the recent week. Okay, so I hope let's make this session interactive. And so before proceeding the session, we will quickly recapitulate what are the things that we have seen in the last week content. Okay, so as this is the first week and the assignment due date is not over, so I will be discussing assignments in the next week. So in this week we will be discussing some questions related to the concept of week one. Okay, so let's move. So the last week we have, like, that is the week one. We begin with the atomistic origin of elasticity. So in this we have seen how the elasticity is related to the atomic structure of a material. Okay, so we got one relation, that is by R naught dt by dr square, where R tends to where or R tends to. Can anyone say? So this is the relation between the interatomic potential and elastic modulus. Okay. So then we commented that the elastic modulus is related to structure of material. Okay. Then later we saw that the stress is directly proportional to. Okay. So in that what they have said that the stress cannot be measured directly. So we use strain because it is really easy, relatively easy to define and also easy to measure. Okay. So the strain is relatively easy to define, and it is defined as the amount of deformation. It is defined as the amount of deformation with respect to the original dimension. So amount of deformation to the original dimension. Okay. So then after that we have seen about about stress. Okay. So we discuss what are the conditions for the stress to be acting on the material. So stress. Okay. So we discuss about the stress. So what are the conditions that are needed for the stress to be acting on the material? Can anyone answer? Hello? Mr. Banerjee, can you confirm? Am I audible?
Yes, sir.
Hello, Mr. Banerjee. Okay. So then we talked about the stress. Okay. So what are the conditions for the stress? As stress, if the stress to be acting on the body, it should be in the equilibrium. So equilibrium is needed. Okay. And what is the stress? It is nothing but the internal resisting force acting against the applied external load. So force against applied external load. Okay. So this we have discussed in the about the stress, and it is expressed by us. It means it is expressed over some area, like it needs some area to be defined. So express by stress acting over a certain area. Okay. So then after that we talked about the elastic and plastic regime of a material. So what is elastic regime of a material? So if the material is deformed and after the removal of the external load, it will regain its original shape and size. So that regime is known as the elastic regime. Okay. Mr. Banerjee, am I audible?
Yes, sir. You are audible now.
Okay, we will quickly discuss we will quickly recapitulate what we have seen in the last week, and then we will move to solve some basic problems which will be related to your weekly assignments. Okay.
Okay,
So,
sir.
okay. So if a material is deformed and after removal of external load, it will regain its shape and size. So that regime is known as the elastic regime. So then we have come across the concept plastic regime or plasticity. So if a material is deformed and after removal of the load, if it will not regain its original shape and size, then that regime is known as the plastic regime. So if a material is deformed and after removal of load, it will not regain its shape and size. Okay, so this is plastic regime. Okay, Then we came across the
Sir,
concept of yeah.
hello.
Yes, Swasti.
Sir, can you please repeat the first formula? The atomistic origin of the modularity.
Okay, so this
Actually,
formula we derived in the our weekly content, and we have one question related to the same how this formula came. Okay, so we will derive that one in our weekly content. So, do you have any questions on this?
no, sir. Actually, this is the potential and the atomic radius. Is this the formula? Elastic modulus is equal to 1 by r naught.
Yeah. This is the formula. This way we can define how the modulus is related to our atomic structure. Like the interatomic potential is related to the atomic bond energy and type of bonding. So how this elastic modulus is related to? So this equation represents the relation between the elastic modulus and interatomic potential. So we will derive this equation. Don't worry. So
Okay, sir. Okay, sir.
so then we came across the concept of uh, interatomic potential. So in that, what we commented, like the stretching during the elastic region is mainly related due to the stretching of bonds. So stretching during elastic regime related to stretching of bonds. Okay. So then we saw one curve that we have plotted against the radius, that is the interatomic radius and interatomic distance and potential energy. Also, similarly, we drawn one curve with force and r naught. Sorry, r interatomic distance. So, what we found? So here we got a curve something like this. Okay, so this is the interatomic potential curve, and it is given by the equation u minus a by rm plus b upon r raised to n. So this considers the attraction, and this consider the repulsion. Okay, so and the distance at which we have the minimum energy, it is the equilibrium distance, and it is denoted by r naught, and this is our
The minimum potential energy.
yes, or we also call it as
Bond
bond
energy. Yeah. Yes, sir.
bond energy. Okay, so if we take a derivative of this interatomic potential, then we get a force F is equal to du upon dr, and it will be something like so b n divided by r to the power n plus 1. Okay, so if we draw the curve for the force versus interatomic distance or the slope of this curve, we will get something like this. Okay, so this is the force curve. Okay, if we move away from like right side on the from the equilibrium distance, the attractive forces will increase, and if we go to the left side of the equilibrium point, so we will get a repulsion force, means maximum repulsion. So this is the optimum distance where the net force is 0. So this is about the potential energy curve. So in this equation we have m and n. So m is usually taken as 6 and n is generally 12. And this curve is also known as the, do you know the name, Swati? 6-12 potential curve.
Yes, sir. Actually, sir, this is the value of the m and n.
Huh?
So it's 6 and 12. It's mainly the value of m and n.
Yeah.
Yeah, yeah, okay, sir.
Yeah, that this is the general value that is there,
Hmm.
and it is also known as the some other name is there for this curve is Condon Morse curve. So in exam they can ask you like that what is the at equilibrium distance in the Condon Morse curve, what will be the force? So easily you can say that at the equilibrium distance the force will be zero. So we seen like how this bond energy is related to the material. So what we have studied is that if the high bond energy is there, okay, the maximum the depth of the bond energy curve, we will get a high modulus. And why is it so? We will discuss in the question. I have put one question regarding the same concept and why is it happening. We will discuss there, and we will get a lower coefficient of thermal expansion. Okay. So then after this concept, we came across the concept of the continuum mechanics. So that defined the stress and strain. So if we consider continuum mechanics, that is a material that is it has a continuity at every point, and it has the uniform distribution of the characteristics. Then we call it as the continuum. So if we consider continuum mechanics, that is continuity at every point and uniform distribution of characteristics. Okay, so based on this continuum mechanics, we define as stress as force per unit. We define stress as force per unit
Area.
area. So remember, if we talk about the normal stress, then the area will be perpendicular to the application of the force, and if we consider the shear stress, then it is parallel to the applied force. So simply we can write F by A, and then we define as the strain, that is change in length per unit original length, that is delta L by L. Okay. So then after that we have taken one diagram like this, the body which is fixed at two ends and loaded with the complex loading. By the concept of continuum mechanics, if I measure the stress at this point, so it will be same for all. So we have taken one element, cubical element, okay, and we represented it as y, z, okay, and there is some stresses applied on its faces. Okay. So then we considered one bar with a dimension of A and B and height, some height like H, and it is loaded with a force F that is equal to W. That is the some weight in the lecture you have seen that instructor has put some weight on the rectangular bar and he considered that force is equal to the weight of that block. So then they have calculated the stress at any random plane oriented at an angle of theta. Okay, so if we draw it here, if a plane is there oriented at an angle of theta, so then this force will will generate some normal stress on this plane as well as some shear stress. Okay, so let's denote, this is the normal stress Fa, and this is the shear force or the tangential force Ft, and this angle is theta. So, and let's say this is our x prime axis, this is our y prime, this is y, this is x. Okay, and then we have calculated the normal force acting on this, that is Fn is equal to, so normal force, that is the cosine component of this force F, that is Fn is equal to F cos theta, and the tangential component will be, anyone?
So F sin theta.
F sin theta. Okay, so then we came across the concept of the representation of the stress. How do we represent? So that is, we represent it using the notation like sigma ij, where I represents the
Solid plane.
defines the plane, and j defines the
Direction.
direction of what?
The direction of the axis.
Direction of the force, in which direction the force is applied.
Okay.
Okay, direction of force. So if the I is equal to j, then it is normal stress, and if I is not equal to j, then it is shear of tangential stress. So based on this definition, we can write the normal stress, that is sigma y prime, that is the force acting on a y plane, that is the stress on a y plane when the force is applied on in the y direction. So it will be like the normal force divided by area, a theta. So what is the area? That is the, let's assume its original area is A and its direction of is cos theta. So Fn by A theta comes out to be sigma yy, because F by A is equal to sigma yy cos square theta. Okay, sigma y prime, and sigma y prime x prime. Okay, so it is, here you can say it is I is not equal to j, that it means it is the shear force. So shear stress. So instead of representing shear stress with the sigma, we can represent it with the tau. So we will not get confused. Okay, so tau y prime x prime is equal to sin theta cos theta. Okay. Then we saw the stress tensor. So why do we call a stress as a tensor quantity? What do you mean by tensor? Can anyone answer? Anyone? Mr. Aarti, Mr. Swati, Mr. Arun? Why do we call a stress as a tensor?
Sir, it may be how many stress applied on a body. This is normal stress, shear stress. Is
No.
all together may be called stress tensor.
No. No, it's not. So anyone? Mr. Arun, Mr. Arti. So see, there are three quantity. One is scalar, second one is vector, and third one is tensor. So the scalar quantity, what does it have? Anyone? The scalar quantity only needs magnitude, whereas vector quantity needs magnitude as well as direction. And a tensor quantity, it needs magnitude, direction as well as the plane of action or the orientation at which is acting. So as you can see, the stress changes with the orientation as well. If we apply some force, it will develop some stress, and that stress is dependent on the magnitude of the force, direction of the force, and as well as the orientation of the plane or the plane of action. So then we came across the stress tensor. So we saw one diagram like this. Here some forces are applied: sigma x, tau xy, tau xz, sigma z, tau zx, tau zy, sigma z, tau yx, and tau yz, and we represented it in the form of a matrix. It is sigma xx, tau xy, tau xz, tau yx, sigma yy, tau yz, tau zx, tau zy, sigma zz. Okay. So all the normal stresses are along the diagonal. So these are normal stresses. And these stresses that I have marked in the orange are the shear stresses. Then we came across the concept of the transformation, stress transformation or the axis transformation. How we, in the if the it is at some orientation, so how we will transform. So that we studied, but that's not much in detail because it is not that much important. So then we came across the concept of principal stresses. So what is principal stresses? Anyone?
Only normal stresses.
So only normal stresses. It means
No shear
Shear
stress.
stress.
no shear stress is acting, and second one is that is the, and the plane of action of principal stresses is known as principal plane. Okay. Then we came across the equation to find out the principal plane, that is sigma p cube minus I1 sigma p square minus I2 sigma p minus I3 equal to 0. So this is the equation to find out the principal stresses. The root of this equation, the roots of this equation gives the principal stresses. Okay. So do you know how this equation has been derived? I think in yesterday's class it has been covered. Am I right?
Yes, sir. Yes, sir.
So no need to repeat, na? Or should I repeat?
No, sir.
Okay. So if time permits, we will discuss it in the end. Okay. And where the I1 and I2 are, and I3 are known as,
Invariants.
why they call known as invariants?
They tend to change, I think.
They don't change with respect to the orientation. Whatever be the orientation of the plane, they will remain same. So they will not change. So that is known as the invariant. So the I1 is no, it is given by sigma x plus sigma y plus sigma z, where I2 is tau xy plus tau yz plus tau zx minus sigma x sigma y minus sigma y sigma z minus sigma z sigma x, and I3 is given as sigma x
Sigma x, sigma y, sigma z
sigma
plus
y
2 tau xy,
plus 2 tau xy
tau
tau
yz,
yz
zx
tau zx minus
minus sigma x, tau yz minus sigma y, tau
tau
zx
yz square minus sigma y tau
x
xz square minus sigma z tau
tau xy square.
tau xy square. Okay. So this is the invariant. That is the I1, I2, and I3. So you should remember this equation. Okay, this will going to help you to solve the lot of problems. Okay. So then, by sign convention, what do we take? We take by convention sigma 1 is greater than sigma 2 is greater than. So for that equation, we will be getting the three different roots. So among the three different roots, the higher value will be assigned to the sigma 1, the lowest value will be assigned to the sigma 3. Okay. So that, and this value should be algebraically greatest value. Whether it is positive or negative, it doesn't matter. Okay. Then we came across the concept of plane stress. So what is the plane stress condition? What is the plane stress condition?
We take only x and y, it knows it.
Okay. And any other definition? Mr. Swati, Mr. Arti? So the plane stress condition is the condition when there is no shear stress is acting in a one plane, or the shear stress in one plane is zero. When shear stress in one plane is zero. So let's consider a very thin element like this. Okay, and if I apply a load in this direction, okay, so and if I take the element out, so you can say that here only the normal stress is acting, no shear stress is acting on this. And here normal as well as shear stresses are acting. Okay, so after that we came across the concept of plane stress transformation. So why do we need a stress transformation? Can anyone answer? Okay. So suppose if you want to find a stress at a particular plane or a particular orientation in the material. Okay, for a simple material, like if it is we want to find out the normal stress to the applied plane, then it will be just simply F by A. But if we want to find out the normal stress at any particular angle, or if the force is applied at an angle, so that time we need a plane stress transformation. So there we have considered the one wedge shape like this. All of you have gone through the lectures, na? So this is the direction of acting of normal force or the sigma x prime. Let's consider, and this axis is x prime, and here we will be having some axis y prime. Okay, and here we have applied sigma x, and this is tau xy, and here we have applied sigma y and tau yx. Okay, so here we will be getting the stress of sigma x prime, and here tau x prime y prime. Okay, so to solve this type of problems, we derived some equation, and finally we got sigma x prime equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. This is for the sigma x prime. Then for sigma y prime, what was the equation? Anyone?
Sigma x plus sigma y by 2 minus sigma x minus sigma y by 2 cos 2 theta minus tau xy sin 2 theta.
Okay. Minus tau xy sin 2 theta. And for the shear stress, it is minus sigma x minus sigma y by 2 sin 2 theta plus tau xy cos 2 theta. So this will be the maximum normal force and maximum shear force acting on that particular plane. So this is about the how we have calculated the how we can calculate the shear stresses and the normal stresses. And what about the orientation? Orientation for maximum normal stress and shear stress is given by equation tan 2 theta. Here I am writing P for normal, and it is given by 2 tau xy
2 tau xy by sigma x minus
sigma y, and here for shear stress tan 2 theta s minus sigma x minus sigma y divided by 2 tau xy. Can you find out any relation between these two? The orientation for maximum normal stress and shear stress.
These are perpendicular to each other.
They are the plane of maximum normal stress and maximum shear stress are away by 2 theta equal to 90 degree. That means theta will be equal to
45 degrees.
45.
45.
Yeah, maximum normal stress and maximum shear stress away by 2 theta equal to 90 degree. That is theta equal to 45 degree. Okay. So this much things we have covered in the last week content. Okay. So now we will move towards the solving some problems. Okay. So why I am recapitulating all these things? Because this will in turn will help you to solve the problems. Okay. So let's move towards the problem. So we will see some concept related questions. So yeah. So here you can see question one is there, that one assertion and reason is there. The assertion is that
So we have done this yesterday.
okay. So this one,
Yes, sir.
okay. What about this one?
This also.
Okay.
This also.
This also you have discussed. Let me check. And 7, 8. This one?
Yes, sir. Not this.
Yeah, this one you have done. Up to this one you have done. Okay. Sorry. Up to this
Up
question.
to 8 only.
Up to
Yes,
8.
sir.
Yeah. So, all were you present yesterday, na? Okay.
Yes, sir.
Okay. So this first 8 question we will discuss later. We will discuss some other question first. Okay. So here.
The 8th question we discussed, I think.
Yeah. So first we will discuss the new questions. Then we will again discuss the same question, because some students might not be present yesterday for them. So here the question is like that.
Yeah, actually, I have doubt that in week third assignment, the date mentioned in like email, it is 8, the deadline is 8. But
Yeah.
in assignment page, it is 15. I have also written email, but there is no response for that.
Yeah, you will get a response soon. Okay, but for first and second assignment, it is 8th February, and for third one, it is 15th. Am I right? I think I will cross check with them and I will let you know. Okay. So the question is like that. The above diagram shows a schematic diagram of a variation of potential energy with separation between two similar atoms. The green line refers to the plot obtained at a room temperature. If the material is heated to a temperature, say T1 is greater than RT, then which of the following represent the schematic of the potential energy curve for T1? So can anyone answer? Whether that is blue line, red line, or none of them, or the information that is given, it is sufficient to answer this question. Anyone? Okay.
Might be the red one.
Might be the red one. So why is it so?
Because on increasing the temperature, thermal thermal expansion generally decreases.
Okay. So, and that is related to?
Potential energy.
Okay. So let's see. So let's consider the potential energy versus interatomic distance curve. Okay. So here, if at a equilibrium we have a distance of r naught at equilibrium. Okay, so let's say at equilibrium distance at room temperature. Okay, let's consider the room temperature condition is r naught. Okay, so at room temperature we have a distance of r naught. Okay, so what will happen if we increase the temperature? So the atoms will vibrate. Am I correct or not? The atoms will vibrate if we apply a temperature, and so what will happen? That vibration of atom will increase the amplitude of the thermal energy, or the amplitude of vibration increases with the thermal energy. So Suppose this is the well. If I increase this is at room temperature. Let's say I am increasing the temperature to T1. So this potential will decrease like this. Like it will move to the A1, B1 at temperature T1. So, okay. So suppose at a temperature T1, amplitude is A1, B1. So now again I am increasing the temperature to T2. Say T1 is greater than T2. So again, this potential will change to A2, B2. So what is happening here? When we heat the material, okay. So there are some repulsive forces and some your attractive forces are there. But when we heat, due to the vibration, the thermal energy will increase and their bond length will increase. Okay, if we heat the material, so they will try to expand. It means their bond length is increasing. Am I correct? So if the at R naught, if at RT bond length is R naught, okay. Let's say this is R1, this is R2. Then at temperature T1, bond length will be R1. At T2, the bond length will be R2. So what is happening? So as I am increasing the temperature, the curve is shifting upwards, as well as the equilibrium is shifting towards the right. So here in this option you can see that blue curve, the equilibrium radius is not changing for the blue curve. Okay, means only the potential energy is changing for that one. So this can't be our option. So we can eliminate. So now see for the red one. For the red one, the potential energy is also decreasing, and as well as your bond length is also increasing here. For the red one, the bond length is at this position. So from the original room temperature to at some temperature T1. So the correct answer will be for this one is the red line. All understood, na? Am I audible? Hello.
Yes, sir.
Okay. You understood, na?
Sir, I have a doubt.
Yeah.
Sir, please tell if my analogy is correct. If we are increasing the temperature, there is going to be a vibration of atoms, right?
Yeah.
So how could we say possibly that there is increase in separation between atoms?
Because
how could there be a change in the bond length?
When we hit the material, there might be some expansion associated with that material. Like if we hit the material, it will expand. Am I correct?
Yes, sir.
Okay. So that expansion, where does it come from? When the bonds of that atoms will the bond length will increase, then at that time only we will get the expansion. Am I correct? If we are not applying any force and this, and we already talked that the stretching of the bonds related in the elastic regime as well. So when we heat, it will get the material will get deformed, means it will expand, and that expansion is due to the change in the bond length. Am I correct?
Yes, sir. Correct.
So now you got it. Why is it happening? Why the bond length is changing?
Yes, sir. I got it. Thank you.
So let me write this for the students who are not attending. So at a equilibrium distance, the distance at equilibrium is r naught. So as we increase the temperature, atoms will vibrate due to thermal energy, and the amplitude of vibration will increase with the temperature. Will increase with temperature. So suppose at T1 bond length amplitude is A1, B1 and radius R1, or the interatomic distance is R1. At T2 amplitude will be A2, B2 and length will be R2. So as the temperature increases, the R naught will increase. Also, amplitude will increase. So, mean the bond means what does it implies? It means bond length is increases on heating the material will exhibit thermal expansion. Okay, so this was about the question. This. So now here comes the question. Can anyone answer? We have already discussed and you have already answered about this question. Yeah, this question. The question is like that. The following figure shows the principal stress on a body in the form of a cube, whose faces are principal planes, and the sigma 2 is greater than sigma 3. So here you can see this figure, and here the sigma 2 and sigma 3 are applied. So what will be the position of a plane? Which of the following correctly represent the maximum shear stress plane? Anyone? Anyone?
First figure.
Huh?
First one.
First one. And any other option?
Second one.
Second one. Okay. So anyone? Any other options? So we have two options. Any third option? Any other option? Anyone? Okay, let's see. Like we have seen that the orientation of maximum shear stress and normal stress are away by
45 degrees.
theta equal to 45 degrees. So the plane should make an angle of theta equal to 45 degree with the your sigma 2 and the sigma 3. Here we are applying sigma 2 and the sigma 3. Here you can see in the first figure it with sigma 2 it is making 45 degree. Am I correct? But with sigma 3 it is making 90. Am I right? Sorry, it is not making 90, it is acting on this plane. Am I correct?
Yes, sir.
And so this can't be our answer. So we eliminate one option. So here it is making 45 degree with the sigma 3, but not with the sigma 2. Yeah. Also, so this can't be our option. Let's come for this one. Here also, it is not making any angle with the sigma 2 and sigma 3. So this can't be our option. Let's come. Here we can see like that. So let me draw the line. So here we are getting 45 degree with this one and 45 degree with this one. Is it satisfying our condition?
Yes, sir, it is.
So this will be our answer. Because we already talked that the orientation of maximum shear stress and normal shear stress are away by theta equal to 45 degree, and it is in the midway between the normal stresses. So only this option has a plane midway between the only this option has a plane in between the sigma 2 and sigma 3, and it is satisfying our condition for the maximum shear stress and normal shear stress. Am I correct? Please respond, guys.
Yes, sir. Yes, sir. Yes, sir.
Is it clear to everyone, Mr. Swati Banerjee?
Yes, sir.
Yeah. So let's come to this question. Okay. Let's try to solve this question. Okay. Sorry, it is not visible now. Now it is visible. Question number 11.
Yes, sir.
Okay. Please try to solve this
Sir,
question.
I have a doubt.
Yeah.
In the announcement page for the week 3, it is mentioned that the last date for submission of assignment is 8, but on the assignment page, it is written 15th of Feb.
So write a mail to the NPTEL team. They will clarify.
So I have already written the mail 2 days before, but there is no response for that.
Okay. I will cross check and I will let you know in the next session. Okay.
Yes, sir. Thank you.
Okay. Please try to solve this question. Determine the principal stress for the state of stress. So which equation should I use here?
Sigma cube minus that one.
Yeah. So we will use equation sigma p cube minus sigma p I1 sigma p square minus I2 sigma p minus I3 equal to 0. Okay, so what is I1? I1 is sigma x plus sigma y plus sigma z. So our sigma x, sigma y, sigma z are our diagonal elements. This is for I1. Am I correct?
Yes, sir.
So let me write this for simplicity. Sigma x, tau xy, tau xz, tau yx, sigma y, tau yz, tau zy, tau y, tau z, tau zx, tau zy, and sigma z. So now, what is the value of sigma y? 200 minus plus
Minus 80.
280. So it comes out to be minus 80, right? Now, what is I2? I2 is tau xy plus
Tau xy.
tau yz plus tau zx minus sigma x, sigma y minus sigma y, sigma z minus sigma z, sigma x. Is it correct? Yeah.
Sir, 110 square term.
Yeah, that tau xy is square. Sorry. So this is square. Yeah, you are correct. So please correct me whenever I am wrong. Okay. So here
Okay, sir.
tau xy is there. How much tau xy is there? It's
Minus 240.
minus 240 square plus tau yz is 0.
0.
Tau zx is
0.
0 plus, or here we have minus sign. Okay, so minus sigma x into sigma y.
Sigma x is 0.
0. Here sigma y into sigma z. So here we have 200
200 and minus 280.
280. And here sigma x is also 0.
0.
So I2 comes out to be, what is the value of I2? Please solve along with me. So what is the value of I2?
So minus 1600.
Yeah. It comes out to be 11,3600. Please cross check. Because here we have minus 240 square.
Yes, sir, it's correct. 113600.
Minus 200 into minus 280. So this minus will get plus and we will get the 113600. Okay. So now we need to calculate I3. So what is I3? Sigma x, sigma y, sigma z.
Sigma z
2
plus tau x, 2 tau xy, tau yz, tau zx.
Tau zx minus sigma x tau yz square minus sigma y tau xz square minus sigma z tau xy square. So now put the value here. As sigma x 0, this whole term becomes 0. Here yz is 0, this whole term 0. Here also sigma x 0, 0. Here we have another term, that is sigma y tau xz. Tau xz is also 0. So now we are remaining with sigma z and tau xy. So tau xy is there. Sigma z is how much? Minus 280.
Minus 280.
Into tau xy square minus 240 square.
240 square.
So how much it is?
16128,000.
16128,000.
128,000.
Okay. Now put this value in the equation. That is, sorry, sigma p cube minus I1 is minus 80 sigma p square minus I2 is 113600 sigma p minus 16128,000 equal to 0. Now solve this equation and please tell me the value of different sigma. Sigma A, sigma B, sigma C. Please solve me. So it comes out to be sigma, first root comes out to be 360 megapascal. Am I correct? This comes out to be minus 160 megapascal and this comes out to be minus 280 megapascal. So, yeah. Am I correct? Any Yogesh, Aarti, Arun, please cross check. Mr. Banerjee, please cross check whether my values are correct or not.
One second.
Are you getting the values, guys?
Sir, can you please solve it?
Just use the calculator and you go to the equation and you just insert the values of coefficient A, B, C, D, and you will get the values, roots of this equation. So here, if you go to the calculator and go to the menu, setup where we have.
Yes, sir. It's coming. Minus 280, minus 160, and 360.
Okay. So now tell me which value is the principal stress?
Sigma 1 is
360.
360 and then minus 160, then minus 280. It will decrease in algebraic order.
So I am asking about the principal stress.
So 360 megapascal sigma A is a principal.
What is the definition of principal stress? The principal stress means where there is no shear stresses are acting. Am I correct? Okay.
Yes, sir.
So instead of solving all this, we could have just looked at this matrix and here only in this phase or where the sigma z is equal to minus 280 there, on that phase no shear stresses were acting. Am I correct?
Yes, sir.
So the simple value we can take as principal stress is 280. So this types of question will comes in GATE. Just by the observation you can solve. Instead of doing all this procedure, we could have solved just this like minus 280. Am I correct? So before solving question, look at the question. Like the trick is in the
Yes, sir.
question. Yeah, they asked about the principal stresses. Yeah. So now, everyone understood this question, na?
Yes, sir.
Yes, sir.
Mr. Aarti, Mr. Yogesh.
Yes, sir.
Okay. Okay. So we will move to next question. The question is like that. An element in place stress is subjected to stresses sigma x is equal to 16,000 psi, sigma y is equal to 6,000 psi, and tau xy equal to tau yx is equal to 4,000 psi, as shown in figure. Determine the stresses acting on an element and inclined at an angle theta equal to 45 degree. So can you solve this question, guys? Please try to
We
solve.
can solve it using by plane stress transformations.
Okay, so use that equation and try to solve. And let me know the answer, then I will solve. So that you will also get, you will have the practice. So what they are asking in that one element is there at an angle of 45 degree. Okay, if I draw that element here, okay, so this is my x, this is my y. So what they are asking the stresses acting on an element inclined at an angle theta equal to 45 degree. So at an angle of theta equal to 45 degree. So some stresses will be acting sigma x prime, and this will our axis x prime. Here we will have axis y prime, and the shear stress is tau x prime y prime. So how we will solve this question? We'll use the stress transformation. So what are the equations that we got? Sigma x prime equal to sigma x plus sigma y by 2 plus sigma x sigma y by 2 cos 2 theta plus tau xy sin 2 theta. Similarly, sigma y prime is equal to sigma x plus sigma y by 2 minus sigma x sigma y by 2 cos 2 theta minus tau xy sin 2 theta. So tau x prime y prime is given by minus sigma x minus sigma y by 2 sin 2 theta plus tau xy cos 2 theta. Am I correct now? We can use this equation. Okay, so
Yes, sir.
yeah, so what we have given, theta is equal to 45 degree. So 2 theta is equal to 90 degree. Cos 90 is 0. Sin 90 is 1. So all the cos terms will become 0. Am I correct? And sine 2 theta is
Sir.
1. 1. 1. So we can simply write sigma x prime is equal to, what is sigma x? It's 1600, 16,000 plus 6,000 by 2 plus here only tau xy is there. How much? 6,000. It comes out to be how much?
$17,000.
Okay, here it is 5,000 is there. 16,000 plus 6,000. It comes out to be 11,000. Am I correct? Plus 4,000. Sorry, this is 4,000. Just cross check once again.
15,000.
Is it correct?
Yes, sir.
Okay. Now sigma y prime is only remaining with 16,000 plus 6,000 divided by 2 minus 4,000. Is it correct?
Yes, sir. 4,000.
4,000.
7,000 total. Sigma y dash.
7,000 psi. Is it correct?
Yes, sir.
Okay. Now we are remaining with tau x prime, y prime. How much is it? Only this term is there. Minus sigma x minus sigma y by 2. So we have minus 16,000 minus 6,000 by 2. So it comes out to be minus
11,000. Sorry, 8,000.
5,000 psi. So sigma x prime is how much? 1,000 psi. Sigma y prime is how much? 7,000 psi. And tau x prime y prime is how much? Minus 5,000 psi. So now if we represent it on the element, so this is our element. So our sigma x, this will be our sigma x prime. Am I correct? Mr. Arun, Mr. Yogesh?
Yes, sir.
And
Yes, sir, correct.
this will be the our
Y prime.
sigma y prime. Here also we have sigma y prime. Here. Sigma x prime. Okay. Now I have the shear stress. That is minus 5,000. So shear stress will be acting here. Am I correct? Why I have
Yes.
kept the downward arrow? You know na? Because it
Yes.
is negative.
Negative.
It is x prime, y prime. And so this shear stress is acting like this one. I have kept it at these two places. So this will create some couple movement. So to restrict that movement, so I will be having another shear stress produced from this side. it will be tau y prime
Y prime X prime.
and this will be tau y prime x prime. So this is the representation of the stresses that we have calculated for the element. Is it clear?
Yes, sir.
Yes, sir.
Yeah. Now this question. How can the Young's modulus be determined from the energy distance curve? Arun, you are asking, try to solve this question. It's very easy. So I will draw the curve for you. This is force, this is R, U, R naught, R naught. So, so we know the relation between the force and interatomic potential. F is equal to du upon dr.
du by dr.
Am I correct? That is am r to the power m plus 1 minus bn r to the power n plus 1. Is it correct? Now, if I calculate,
Yes, sir.
so this is giving us the force. If I calculate the force, the slope of force curve, so it will come out S is equal to df upon dr. Am I correct? Dou to u upon dou r square when r equal to r naught. Am I correct? Arun? Mr. Banerjee?
Yes, sir.
Mr. Yogesh, Mr. Aarti. So you got this point now, how df by dr is equal to d to u by dr square. So this is our slope or steepness also we can call. Okay. So now if I have a material like this, okay. So these are my atoms. Let's consider at these places. Okay. So now and I am applying force capital F. Am I correct? So now this Fa is nothing but
Load by area.
sigma into A. Okay, like stress that is we are considering on the whole body. Now, if I am considering the force on the individual atoms, so it will be the small f equal to capital F equal total force will be equal to the forces on individual atoms into
Number of atoms.
number of atoms. Okay, and similarly the sigma, the stress will be our force by area. So the force will be small f into number of atoms by area. Okay. So let's consider sigma is equal to f upon r naught square and multiplied by some constant. So that will take care of your the number of atom divided by area. Okay, that k by r naught square. Okay, now consider the strain. Strain will be given by change in length minus original length. Here, how much distance changing? Let's say their original is r naught and they are moving to the some distance r. So it will be r minus r naught divided by r naught. Is it correct? So can I write this as del epsilon is equal to del r because the difference is there and r naught?
Yes.
Yeah. So now we know elastic modulus is nothing but the stress upon
Stress by strain.
strain. Okay, when this is for the bulk material. Now we are considering the small individual item, so it will be df upon d epsilon. When epsilon is very small, means epsilon tending to 0. This is the stress. Okay, so now put the value here. That is f upon r naught square upon dr by r naught. So we got a equation like E equal to df upon d epsilon, epsilon tending to 0 equal to df upon df by r naught square divided by dr by r naught.
Sir, excuse me.
Yeah.
Sir, in the first step, E equal to D sigma by
E which
D. Yeah, here only.
here
Start.
okay.
No. Next slide.
Next slide. Okay.
D sigma by D.
D epsilon, that is the stress versus strain. Stress by strain.
No, sir. In the stress, df is supposed to be D sigma, no, sir. Stress.
Yeah. You can write D sigma, no problem. I'm just considering for small, so I'll change the notation. So okay.
Okay, sir.
So here, so just simplify this one. You will get 1 upon r naught df by dr when r tending to r naught. Yeah. Is it correct? Then 1 by r naught is equal to, we have already derived this term, that is df upon dr is equal to dou to u upon dou r square. So it will be dou to u upon dou r square when r tending to r naught. So here we can see that this E, elastic modulus, this E is related to the electronic structure of the material or the bond energy. So this is how we can calculate the Young's modulus from the energy distance curve. So you were asking like how we have derived this equation. Am I right, Mr. Arun? Mr. Arun?
Yes, sir.
So now you got it now, how we have derived?
Yes, sir. I got it.
So this relation indicates that the elastic modulus is directly dependent on electronic structure of material, or in simple word, what we call bond energy. Okay, so now moving to the next question. So the question is like that: the state of stress is given by sigma x is equal to 25p and sigma y is equal to 5p plus sharing stresses tau x y prime on plane at 45-degree counterclockwise to the plane on which sigma x acts. The state of stress is 50 megapascal in the tension and 5 megapascal in shear. Determine the values of sigma x, sigma y, tau xy. So how we'll calculate?
So by using plane stress transformation, the formulas.
Okay, so try to solve this. So we will use this equation. Shit, yeah. So sigma x prime is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. As theta is equal to 45 degree, 2 theta will be 90 degree, cos 90 0, sin 90 1. So here the cos theta, this term will be 0. Now what we have given is that sigma x prime is equal to 50 MPa. Sigma x is equal to 25p and sigma y is equal to 5p. Now try to solve. So what we will do, we will keep 50 is equal to 25p plus 5p by 2 plus tau xy is given as, no, they have not given the tau xy, so tau xy. So what we will get? 15p plus tau xy is equal to 50. Okay, and we have also the second equation, tau x from y prime is equal to minus sigma x minus sigma y by 2 sin 2 theta plus tau xy cos 2 theta. So we'll simply put the values, that is tau x prime y prime is given as 5 is minus 25p minus 5p divided by 2. So we will get like 5 is equal to minus 10p, and p is equal to please tell me the value of p. Mr. Arun, Mr. Yogesh.
minus half.
Okay, guys, one correction is there. So this is given in MP, and we don't know of the unit of that P. So we will take this in Pascal only. So this will be 50 into 10 raised to 6. 50 into 10 raised to 6. So here also we will have now tell me the values. Here we have P is equal to
minus 5 into 10 to the power 5.
So P is equal to minus 5 into 10 to the power 5. Okay, so now put this value here. You will get tau xy. So tau xy comes out to be, tell me the value. Tau xy is how much?
The fifth.
Please cross check. And sigma x is equal to 25 into P. So 25 into minus 5 into 10 to the power 5. It comes out to be minus 12.5 MPa. Sigma y, it's 5p. It will be minus 2.5 MPa. Please cross check these values. Are you getting the same? Mr. Arun?
Yes, sir.
Okay.
Yes, sir.
So what else is remaining in this question? We have calculated the sigma x, sigma y, tau xy, and the only one thing is remaining, that is sigma y prime.
Y prime.
So use the same equation. Now you have the values of sigma x, sigma y, and tau xy, and tell me the value of that sigma y. So sigma y prime comes out to sigma x plus sigma y by 2 minus sigma x minus sigma y by 2 cos 2 theta minus tau xy sin 2 theta. So sigma x is how much? Our minus 12.5 minus sigma y is 2.5 by 2. So cos 90 is 0. So this whole term becomes 0. So only we left with minus, and sin 90 is 1. So this is minus tau xy. How much is tau xy? Or 57.5. Now tell me the value of sigma y prime.
Minus 65.
Minus 65 megapascal. So this is how we have calculated the answer to this question. So now we'll go to the previous questions that we have skipped. So coming here, right, they have asked the other.
Sir, can you please share the slides from question 12 to 14 as I couldn't join due to network issue?
Yeah. This will be provided to you on the course website. Don't worry. So the question is like that: the repulsive force between the atoms is much larger than the attractive force. The superimpose of the electronic orbitals is the reason for the repulsive force. So which of the following options are correct? Both the assertion and reason are false. The assertion is true, but the reason is false, and both the assertion and reasons are true, but the reasons is not correct explanation of the assertion, or both the assertion and reason are true, and the reason is correct explanation of the assertion.
The fourth
The
one.
both assertion and reason are true,
Why is it so?
and reason is the correct explanation.
Okay. So if
Because in the force separation graph, the repulsion region dominates, so it will have a much magnitude than attractive force.
yeah, correct. So here, if I have a force R. So here, as you can see from the interatomic potential curve, if we draw the forces, so if we move to the left side, it is showing the repulsive force. Okay, and this is attractive force. Here you can see that the stiffness of the repulsive force is very much higher. Means it is quickly changing. Okay, the small change in also it's called. Hello. Hello. Is it screen visible?
You are audible, sir.
Okay. So is it screen visible?
Yes.
So is it? Oh shit. So here if we move towards the left, the repulsive forces are becoming dominant. So why is it so? When we consider the nucleus and electrons up to atoms, so this will overlap with each other. The electron will repulse, and the nucleus will repulse each other if they come much closer to each other. So the assertion is like that: the repulsive force between the atoms is much larger than that of the attractive force, and the superimpose of the electronic orbitals is the reason for the repulsive force. So here both the assertion and reason are correct. So the option fourth will be the correct one. Is it correct?
Yes.
So now
Yes, sir.
toward the second question. The figure shows the state of stress on a body in a plane stress condition. The hint, we can use the Mohr circle, but as the concept of Mohr circle is not discussed, we will solve the problem using our old method. So how can we solve this question?
Using the cubic equation of principal stress.
Okay. Any other method also? Is there any other method?
There is other method also.
Okay. What is that one? Okay. We will solve by both the methods.
There is separate equation for the principal stress and the shear stress and the angle between them.
Okay. Okay. So here we will solve by both the methods. Okay. So here sigma x is given as 8 MPa, sigma y is 2 MPa, and tau xy is 2.7 MPa. So we'll use the equation sigma p cube minus I1 sigma p square minus I2 sigma p minus I3 equal to 0. So what is I1? Sigma x plus sigma y plus sigma z. So what is sigma x is 8 plus 2 plus 0. It comes out to be 10. Is it correct? Now, coming to the I2. I2 is tau xy square plus tau yz square plus tau zx square minus sigma x, sigma y minus sigma y, sigma z minus sigma z, sigma x. Are you getting this, guys?
Yes, sir.
Yes, sir.
So as sigma z is not there, so these terms will become 0. Here also zx 0. So only we are left with the terms tau xy square, that is 2.7 square minus we have that one sigma minus sigma x. Sigma x is 8 into 2. So this comes out to be minus 8.71. Am I correct? And the third one is our I3, that is sigma x, sigma y, sigma z plus 2 tau xy into tau yz into tau zx minus sigma x tau yz square minus sigma y tau xz square minus sigma z tau xy square. So here, as in I3, all the forces in stresses in element in the z directions are 0. So I3 becomes 0. Now put this value in the above equation. So we will get equation like sigma p cube minus 10 sigma square minus 8.71 sigma minus 0 equal to 0. Now tell me the roots. We will get sigma A, sigma B, sigma C.
Sigma is 9.036.
9.036. Then
Sigma B is 0.964.
0.964 and
And sigma C is 0.
0. So what they are asking, the maximum principal stress on the body and the minimum principal stress in the body. So as we are considering the case of plane stress, so sigma 3 will not be there. Okay. So by convention, we consider sigma 1 is greater than sigma 2 is greater than sigma 3. As this is the case of plane stress, we are not considering sigma 3. The which one is the sigma 1 then? Is 9.036 and sigma 2 is 0.964. So the maximum principal stress on the body is 9.036 and the minimum principal stress on the body is
0.964.
964. Okay. So now coming to the next part, that is the similar problem we can solve using the equation sigma 1 2 is equal to sigma x plus sigma y by 2 plus or minus sigma x minus sigma y by 2 whole square plus tau xy square. So sigma 1, sigma x is 8 plus 2 by 2 plus or minus 8 minus 2 by whole square plus 2.7 whole square. So 8 plus 2 is 10, 10 divided by 2 is 5 plus or minus under root 8 minus 2 is 6, 6 by 3 is 9 plus 2.7 square is 7.29 and it comes out to be sigma 1 comes out to be 9.0360 and sigma 2 is 0.964. Please cross check guys, are you getting the same values or not? Arun, Mr. Banerjee, Yogesh.
Yes, sir. Values are true same.
Okay. So the next part of this question is the orientation of the axis of the principal stresses with the xy axis is in degree. So the maximum normal stress is given by tan 2 theta
Tan 2 theta p equal to 2t tau x
y divided by sigma x minus sigma y. So 2 into 2.7 sigma x is 8 minus 2.
8 minus 2.
So this comes out to be 2 theta comes out to be 5.4 divided by 6 and its tan inverse. It comes out to be 41.98 degree. Therefore theta is 20.99 degree. So theta will be 20.99. Now what they have asked is tau max, the maximum shear stress on the body is in MPa. So how we can calculate?
Sigma 1 minus sigma 2 by 2.
Okay. So as this is the case of plane stress, then only we can take sigma 1 by sigma 1 minus sigma 2 by 2. If it is not a condition of plane stress, then we have to take a sigma 3 by 2, or which will be comes out to be the maximum. So we can solve it by using two methods. Tau max is equal to sigma x minus sigma y by 2 whole square plus tau xy square, and it is comes out to be root 9 plus 7.29 or 4.0360. Or we can take tau max is equal to sigma 1 minus sigma 2 by 2. It is 9.0360 minus 0.964 divided by 2. So tau max will be 4.0360. So both the by using both the method we will get the same answer. So it will be 4.0360. So now the next question.
Hello.
Yeah.
Sir, for 3D or without plane stress condition, what would be the tau max?
So it will be the difference between sigma 1 minus sigma 2 by 2 or sigma 2 minus sigma 3 by 2 or the another difference, and whatever out of this will be the maximum, that will be the maximum. That will be the tau max. So I think in the upcoming lectures, sir will tell in the more circle. So don't worry about it. As this concept is not discussed in the previous week, but this is just for your additional information. So sir will cover this content in next week. More circle. In more circle, he will talk about this. Why we are considering tau max as a maximum of that.
Okay, sir.
So now coming to the question 6. That is, the question is like that statement. At equilibrium distance, the force between the two atoms is minimum, not necessarily zero. Statement 2 is at equilibrium distance, the potential energy is minimum. 3. At equilibrium distance, the force between the two atoms is zero. And fourth one is at equilibrium distance, the potential energy is zero. So which of the above statements are correct? Can anyone? So I will draw the potential energy curve for you so that you can easily answer. Yeah, guys, now try to answer.
Actually, the force between the two atoms should be zero at equilibrium, not minimum. And the potential
energy must be minimum.
energy is minimum, not zero.
Not zero. Okay. So, as we all know, the interatomic potential is given by A by minus A upon Rm plus B upon R to the power n. So now, if we consider the force, that is du upon dr. Okay. So when du upon dr is equal to 0, what will be the condition? That condition will be either
R equal to R0. R is equal to R0.
R equal to R naught. So what they are asking, that at equilibrium distance, the force between the two atoms is minimum, not necessarily zero. So if we consider that is df, that slope of the force curve, df by dr is equal to dou to u by dou r square. So if dou f by dou r is zero, then dou to u by dou r square equal to 0, and our f is equal to 0. So at the equilibrium distance, the force between the two atoms is minimum, not necessarily 0. So but at the equilibrium distance, the force comes out to be 0. So this statement is wrong. The second statement, at equilibrium distance, the potential energy is minimum. Is it correct? Yeah.
Correct, sir.
It's correct.
Correct.
The third one is at equilibrium distance, the force between the two atoms is 0. That we have already proven. So this one is also correct. Then At equilibrium distance, the potential is energy is zero. Is it zero?
Minimum.
So this is not. So only the correct options are statement 2 and 3. So here both S2 and S3 are correct. So this was about the week 2 content and some concept related questions. So in next week content we will discuss the assignment 1, okay, and some more questions related to the concepts of week 1 and week 2, okay. And if you have any doubt you can ask, or we will end our session here and we will meet in the next session next Tuesday.
Sir,
So we
hello.
yeah.
Sir, I have one doubt. In the last question, why is it necessarily we should take that sigma 1 minus sigma 2 as the maximum shear?
So
Why is it like that?
in week 2 content you will get the answer. Like if you watch the videos, like more circle, and that in that they have explained very well. So if not, then we will discuss it next week.
Okay, sir. Thank you.
Okay, so we have the sessions Monday and Tuesday evening. Okay, so you can attend any sessions. So there is no issue. Almost the content will be the same, not necessarily, but yeah. Yes, sir, Mr. Banerjee.
Yes, sir.
Yeah.
So can you repeat the concept of the very first question of that session?
Huh?
The first question of that session, can you repeat the concept again?
Which one?
Bond length was so during heating a material, the increasing the bond length. That question.
Okay. So just let me go to that question. Yeah, this one, na? Yeah. No.
The previous one.
Yeah.
Yes, sir.
Yeah, this one.
So how can the red color the graph? How the red graph shift a little towards right?
Let's see, this graph you can see here. I am marking. Okay, so this graph. So let's suppose at equilibrium distance, at room temperature, our equilibrium distance is R0. Okay.
Yes, sir.
Yeah, R0 is there. So when I heat the material, the atom will vibrate due to the thermal energy.
Yes,
okay.
definitely.
Yeah, and the material will expand.
Yes, sir.
Material is expanding means its bond length is increasing. So here I have shown that here in this curve here I am marking in this curve. You can refer to this curve here. The red dots, the radius is increasing. Radius is shifting towards the right. Sorry, interatomic distance is shifting towards the right. Am I correct? As I am hitting the material, so it will expand. So suppose at temperature T1, it is having some interatomic distance as R1. So if I hit it to the temperature T2, this is T2, so it will have the R2. So means while hitting, the atom will vibrate due to the thermal energy, and the bond length will increase with increase in the temperature. So here in this option, you can see the blue one, the blue curve is having the same bond length at the room temperature as well as the temperature T1. But in the question,
yes, I got it.
They have asked that they have mentioned that T1 is greater than room temperature. So our interatomic distance should shift towards the right. So only in the red curve, the interatomic distance has shift towards the right. So that's why this option. Okay.
Yeah, got it, sir.
So we will meet next week. Okay, guys.
Sir, please share the slides between question 12 to 14.
Yeah. You will definitely get the slides for this. Yeah. So we'll meet next week, guys. So see you again.
Sir, yesterday I wasn't able to attend. So will the yesterday session notes?
Yeah. In the course website, you will having be the video live session option below that week 1, week 2. So from that you can access the recordings.
Okay, sir.
Yeah. So see you guys next week.
Thank you so much, sir.
Thank you
Thank
for
you, sir.
okay.